Hello students, so today we can discuss another important boron compound, that is boron nitride. Boron nitride, which is represented as Bn. So like our uh, carbon, and now we know carbon having two important allotropes, that is now one is diamond and allotropes. Similarly, boron nitride have very much closer property with this now diamond and graphite, where now you will see diamond is the hardest substance and we can see boron nitride is the second hardest substance. So there are some similarities there between the property of this diamond graphite and this boron nitride. So let us check the structural point of view first, where boron nitride and this allotrope of carbon actually are having structural similarity, isoelectronic structure. You can see what does it mean about. We know the structure of diamond is carbon is bonded to four other carbon atoms. So now surrounded to each carbon atom there will be 8 electron is there, right? 8 electron will be there. So you can see the valency of carbon is 4. So around a particular carbon atom there will be 4 more electrons. So 8 electrons surrounding one particular carbon atom. Similarly, if you check boron nitride, where boron having a 3 number of valence electron, where nitrogen having 5 number of valence electron. So 5 plus 3 8. So again now similarly you can see the in boron nitride there are each atom is surrounded by 8 electron. So in that sense they have a isoelectronic structure with respect to the allotrope of carbon. That means if you compare the property, it coming very much closer to the properties of this diamond and graphite. So there are now two important crystalline form of carbon, that is diamond and graphite. Similarly, boron nitride have two important polymorphic structure that we will call hexagonal boron nitride and cubic boron nitride. Where cubic boron nitride now having very similar property with respect to diamond, and hexagonal boron nitride now very much similar property to graphite. So you can easily learn this through by understanding or remembering the structure of diamond and graphite. Where now diamond we know each carbon atom is sp3 hybridized, and now it's a very strong material that we have seen. It's one of the hardest substance. So each carbon atom is tetrahedrally surrounded by 4 carbon atoms. Similarly, in cubic boron nitride, you will see each atom tetrahedrally surrounded by 4 other. Each boron is tetrahedrally surrounded by 4 other nitrogen atom. Similarly, each nitrogen atom is tetrahedrally surrounded by 4 other boron atom. So like that now, the structure that generally we know we draw for diamond, very much the similar structure for the cubic boron nitride as well. So there now one difference it will be boron and nitrogen. So when you draw the structure of diamond, sometime we will draw something like this, where now this is tetrahedrally surrounded. So now you have to imagine three-dimensionally. So each carbon atom will be bonded to 4 other carbon atom. Here now I am just showing like this. Okay, like that it will extend three-dimensionally. Similarly, the difference will be here, instead of carbon it will be boron and nitrogen. So boron, nitrogen. Like the way the cubic boron nitride structure will develop. Okay, each boron atom tetrahedrally surrounded by 4 other, like this. 4 other boron atom, and each boron atom tetrahedrally surrounded by 4 other nitrogen atom. So that's the way the structure of cubic boron nitride will be, and like the hybridization, the carbon atom in a diamond is sp3 hybridized. Similarly, each atom in cubic boron nitride is sp3 hybridized. And if you talk about the hardness, diamond is of first highest hardest substance, followed by second hardest substance is cubic boron nitride. So hardness is there, is very much structural, also electronic. So structure also looks similar, the electronic structure also looks similar. So much similarity is there between the structure of diamond and the cubic boron nitride. Okay, so that's the way you can remember this, no, one of the polymorph of boron nitride, this cubic boron nitride. Similarly, now you can imagine a graphite. Graphite, now we know graphite have a hexagonal layer structure. Graphite have a hexagonal layer structure. That means now you can imagine a hexagonal structure where now each will be carbon atom, and you will see it's just like, you know, different layers. This is one of the upper, just like, no, different pages. This will be one layer, and bottom you will see another layer, like that. You have a layered hexagonal structure. Okay, so that's the way you will see the structure of graphite. Similarly, you will see a layered structure, hexagonal layered structure you will observe in graphite, similar to the hexagonal boron nitride. So the difference will be, instead of now carbon, here it will be alternative boron and nitrogen atom, and if you compare the bond length and uh, the distance between the two layer, you know, they almost look similar. For example, the distance between in case of boron and nitrogen, the bond length is coming around 145 picometer, and we know two layers are attracted each other by van der Waals force. So if you talk about van der Waals radius, it's coming around 333 picometer. So if you compare with this graphite, this hexagonal boron nitride have very much similarity with the hexagonal layered structure of graphite. So here now you will see alternative boron and nitrogen atom. So that will be the difference. Okay, that's the way the structure will develop. Okay, so that is the two important similarity between the hexagonal boron nitride and cubic boron nitride. Okay, these are the two important polymorphs of boron nitride. So now let us discuss the preparation. Talk about preparation. Yes, now it is easy to prepare hexagonal boron nitride first. First we prepare hexagonal boron nitride, then this hexagonal boron nitride is converted into cubic boron nitride. That's the way now we synthesizing the two polymorphs of boron nitride. So let us discuss how hexagonal boron nitride prepared. First from diborane. B2H6 diborane, now when heated to high temperature in presence of ammonia, excess of ammonia and temperature above 300 degrees Celsius, very high temperature above 300 degrees Celsius, you will see this boron nitride will be formed. So that's the method of preparation of boron nitride from diborane. Okay, remember the hexagonal boron nitride you are going to get first. Hexagonal boron nitride you are going to get from the heating diborane in presence of excess of ammonia. Similarly, another method is from boric oxide. This is the first method. Second method from boric oxide, B2O3. When B2O3 is now heated in presence of ammonia, the temperature is so high, around 1000 degrees Celsius. So when boric oxide heated in presence of ammonia, you are going to get boron nitride. Okay, as the compound, then water also as the surprise. That's the second method from boric oxide, again treating with the ammonia. Now next form from boric oxide, again this time no, heating in a mixture of carbon and nitrogen in a electric furnace. So B2O3 heated in presence of carbon and nitrogen in an electric furnace. You're going to get boron nitride and carbon monoxide will be eliminated. Boron nitride and carbon monoxide will be eliminated. So these are the three important methods of preparation of boron nitride. Remember, in every cases, no hexagonal boron nitride is prepared. Hexagonal boron nitride is prepared. This hexagonal boron nitride, now when heated to very high temperature and providing very high pressure, the pressure around now 5 to 18 gigapascal. 5 to 18 gigapascal, and the temperature is coming around 1730 to 3230. Such a high temperature, if you provide, you will see hexagonal boron nitride will be converted into cubic boron nitride. So we first synthesize hexagonal boron nitride, which you can convert into cubic boron nitride by providing very high temperature and very high pressure. So that is a method of preparation of the hexagonal boron nitride and cubic boron nitride. Hexagonal boron nitride are synthesizing from diborane by treating with the presence of excess of ammonia and high temperature. Similarly, from boric oxide by treating with ammonia at high temperature and in presence of carbon and nitrogen mixture in an electric furnace, you are going to get hexagonal boron nitride. After getting hexagonal boron nitride, we are converting into cubic boron nitride at a very high temperature and pressure. So that is the preparation of hexagonal boron nitride and cubic boron nitride. Now properties. Talk about properties. Yes, I told now it's the second hardest substance, a white crystalline solid, and it's now thermally highly stable. That's something that now you have to remember. It's used for the application where now high temperature resistance is required. So especially now this crucible, which is now generally we use in our chemistry lab, where it can withstand temperature above 1000 degrees Celsius. So it's chemically inert, it do not degrade, and it do not react with the substance that taken inside the crucible. So that suggests no its chemical inertness and high temperature resistance. So it's such a excellent thermal and chemical stability. That's something now you can remember about boron nitride. That why now ceramics and other high temperature resistant materials are prepared from boron nitride. And if you talk about now the cubic boron nitride property, its application is in machine cutting tools and abrasives. So that you can imagine, like no diamond, it has very much harder. Talk about not stability, that I told is highly stable, and it is used for making crucibles and wear resistant coatings. So that are the points you can remember about cubic boron nitride. Similarly, hexagonal boron nitride, like graphite, no, this hexagonal boron nitride have a lubricating property and it can withstand high temperature. That why now its application coming as high temperature resistant lubricant, high temperature resistant paints. It's no, it used there, and high temperature special resistors are prepared from hexagonal boron nitride. If you know one difference that you have to imagine between hexagonal boron nitride and this graphite is graphite is an excellent conductor. It's electrically conducting in nature because of the delocalized free electron that is now present in graphite, where now carbon is sp2 hybridized in graphite. So one electron is free in each carbon atom that delocalized throughout the structure, which makes them a electrically very good conductor. While now in boron nitride, hexagonal boron nitride, there is a significant electronegativity difference between the boron and nitrogen atom. So boron nitrogen atom is polar, hence now because of that polar nature, no electrons are not delocalized throughout the structure. Hence now boron hexagonal boron nitride is not a good electrical conductor, while graphite is a very good electrical conductor. That's something now you can remember as a main difference. Otherwise, now if you look at the structure and properties, everything is very much similar to the diamond and graphite. With respect to this cubic boron nitride and hexagonal boron nitride respectively. So, and another important application, if I say because of this softness and lustrous property, now it is used in cosmetics and personal care industries. That's something that you can remember. Okay, because it's non-toxic and non-hazardous, hence now it's used in polishes, lipsticks, and creams, etc. When it has a light reflective property as well. So anything darker or something is there in their skin will not be appear because of the light reflective property. Okay, so wrinkles will be less visible on your skin by the application of this boron nitride. So softness and lustrous are the other important properties that you can remember about boron nitride. So powdered boron nitride has an application in our cosmetics and personal care industries. Okay, so these are the point you can remember about now this boron nitride. So another important boron compound. So that sums up the important now compounds of boron. Now let us move to the next section, that is now structure of aluminium chloride. Talk about now aluminium chloride. The first point you can remember about aluminium chloride is now you only need to learn the structure. Aluminium chloride, now if you look at uh, the trigonal planar structure of aluminium chloride, now aluminium having now 3 electron in the valence shell, 2 8 3 electronic configuration. So you will see aluminium chloride now more covalent in nature, because now according to Fajan's rule, we have studied smaller the size of the cation, covalent character will increase. So aluminium chloride more of a covalent behavior, where you will see only 6 electron around the aluminium atom. So according to octet rule, no, this generally unstable. So it can act as a Lewis acid, where have a tendency to accept a pair of electrons. So aluminium chloride are very good Lewis catalyst, where it can accept a pair of lone pair electron. So that one aluminum chloride in the AlCl3 form is actually unstable. That's why it exists as dimer. So usually you will see aluminum chloride in a dimer form in below 400 degrees Celsius. In the vapor phase it is isolated. So dimer form is all about now aluminum is bonded to chlorine atom, where you will see now AlCl3 plus AlCl3. So having a Al2Cl6 form. Okay, that's a dimer form. Two AlCl3 are combined form. Where now you can see aluminium only have 3 electrons. So let me represent these are the 3 electrons of aluminium, if you imagine. So there is now this bonding actually coming from now it's a coordinate bond between chlorine and aluminium. Where now chlorine having actually having now 7 electron in the valence shell. So a pair of electron can be utilized for the bonding with this aluminium atom. So 7 electron in the valence shell. So 2 plus 2 4 5 6 7. So now one pair of electron is actually utilized for the chemical bond, coordinate bond formation between AlCl, aluminum and chlorine. That's the way now the bonding will be, where now uh, aluminium chlorine aluminum bridge bond you will see, where now a pair of electron is contributed entirely from one of the chlorine atom. This is a normal AlCl covalent bond, other will be coordinate bond. So that's the way the structure of dimer will be, something that you can remember. Talk about the AlCl3 trigonal planar structure. Yes, this structure is also isolated at a very high temperature above 800 degrees Celsius. Now this is AlCl3 in the trigonal planar form, that is now sp2 hybridized AlCl3 form, that is also isolated. That's something that now you can remember. Okay, in the vapor phase this is isolated. So these are the now important points you can remember about aluminium chloride. Okay. So in the next class we can discuss what are the oxides and oxoacids of group 15 elements. Okay. Thanks for listening. Let us wind up.